So let's do another example with the cars again. So if you have noticed in Formula One races, if you have ever watched them, I'm not a follower of them, but if you watch them, you will realize that when the cars enter a curve, the road is not flat. They are tilted a bit. Now the problem we had, okay, if you imagine a car moving with some velocity, it's trying to make a right turn. So if we had obtained that the maximum velocity that the car can have without sliding is, well, this symbol, by the way, is called mu. The coefficient of static friction times the gravitational acceleration times the radius. Mu s. Mu is mu. This is the name of. So if it goes faster than this, the car will not be able to follow the curve because there will not be enough force to change the direction of the velocity of the car in order to follow the curve. So this is what it means. Well, there was a question asking me, why doesn't the mass make any difference in that? There is no mass here. Whether you have a very light car or a very heavy car, they all have this same maximum velocity. Any ideas? Why the mass doesn't appear there? We know that if the mass is heavier, if the object has a larger mass, then the normal force will be larger. And since the normal force is larger, the the friction force will be larger. So shouldn't it be that a larger car can more easily take the curve without skidding? Somebody else? Nobody? So the question is this. Suppose we have a light car and a heavy car. They are moving with some velocity v, and they would like to take the same curve with the same radius of curvature. Okay, so that is good. No, okay, the friction force is increasing, so it should be easier for the heavier car to take the curve, no? What is the same? That is what we had found, but why? Why? Not a bigger acceleration, but a bigger force to create the same acceleration. So its inertia is also large. So in order to, is that the word you were looking for? So in order to change the direction of the velocity, you need a larger force if the car is heavier. So that is why, at the end, these two effects, the increase in the friction force and the increase in the inertia, they cancel, and the maximum possible velocity that the car can have that will allow it to go around the curve without skidding is independent of the mass. So suppose you are a road designer. You are designing roads for the Formula races, and you would like your cars to be able to go faster than this speed around the curves. So what you should do? Downforce? I mean, how will the road be applying a downforce? By? But you are not a car designer, you are a road designer. You are building the road. Yes. So here, remember, there are three forces acting on my car. There is the friction force. Well, we can affect the friction force by modifying this mu s, or by modifying there's also the normal force. either modifying μs or the normal force, we can modify the friction force. There is the weight, and there is the normal force. The weight will always be pointing downward. There is nothing we can do about that. The weight will never have a component towards the center, but we can change the direction of the normal force. We can make sure that the normal force has some component in the direction of the center of the curve by tilting the rod. So rather than using this rod, such a flat rod, horizontal rod, we can use a tilted rod. Now, in the case of a tilted rod, even in the absence of friction, the car can just make this turn. It is possible for the car to make this turn. So let us calculate that one. So we have our car. Let's assume that this angle is theta. Then we know that there is a normal force. There is also the weight of it. Now the question is, what should be the velocity of the car so that the car will be able to go around the curve even in the absence of friction? Now in this case, if there is no friction, there is no way the car can take that turn, because it is only the friction force that is causing the change in the velocity. It is only due to the friction there is an acceleration towards the center. In the absence of friction, there will be no acceleration, and so the car cannot go around the curve. But in this case, we already have a force towards the center, which is the normal force. The normal force has a component towards the center. So let us write the components. Well, let us first draw the free body diagrams. We have the normal force, and we have the weight. Let's choose our axis. This will be my x-axis, this will be my y-axis. This angle here will be theta. So I can write down the forces in terms of their components. The normal force will be its magnitude times sine theta in the x direction. Well, in the x direction, it is this component. This length is n sine theta. It is on the x direction, plus n cosine theta. It is the length of this side. It is in the y direction. This is my normal force. The weight is mg in the minus y direction. This is my mg. So these are all the forces acting on my system. The total force will be equal to n cosine theta minus mg in the y direction. I'm just summing these two, plus n sine theta in the x direction. This is my total force. Now the acceleration of my object, of the car, will be in this direction. This is the acceleration. It is towards the center of the curve. Now the acceleration is in the x direction, and it is magnitude in terms of its speed, and the radius of curvature is given by v squared over r in the x-hat. I have the total force acting on my mass. I have the acceleration of the object. And again, Newton's second law just tells me that these two are proportional to each other. So F total has to be equal to mass times the acceleration, m v squared over r in the x-hat direction. I have the expression for the total force. I have the expression for the mass times acceleration. I just need to equate these two vectors. Well, equating the x components, I know that on this side I have mv squared over r. On this side I have n sine theta. The y components, on the other side, I don't have anything. The y component is 0. On this side, the y component is n cosine theta minus mg. So mg has to be equal to n cosine theta. I have two unknowns. I don't know n, and I would like to find theta in terms of the speed and the other parameters of the problem. So I can eliminate n by dividing these two equations side by side, and they will cancel. So I will end up having tangent theta should be equal to, well, the masses also cancel, v squared over gr. This is the equation. If somebody tells you that you are supposed to design a curve such that the cars should be, it should have a radius of curvature given by r, and the cars should be able to go around this curve with the speed v, even in the absence of friction, then this is your experiment. This is the angle that you should have in the curve. Now, of course, in this case, the cars can go even faster than this one, this velocity, because in real life there will be friction. If the cars go faster than this velocity, there will be additional friction force in this direction, which will hold the car in place. So the car will not skid. Even if it goes faster than this, the car will not skid out of the road. Only gravity, no friction force in this case. This is called the banking angle. This is the angle that a car of this speed can take the curve without skidding, even in the absence of friction. Then you can ask, what is the maximum speed then? In this case, suppose you have built a road with this banking angle. So what can be the maximum speed a car can go around this curve without skidding? Now let's solve it. This is the angle theta. At the maximum velocity, I know that there is a friction force keeping the car on the road in this direction. And, well, I should add that force here. There is this force, a friction force. And the angle is, the normal force is normal to the surface. The friction force is along the surface, so here I have a right angle. So this angle over here is also theta. Now the steps are always identical. You have this problem. Identify the forces, draw the free body diagram with the forces. Then you always write the forces in terms of their components. Let's start with the normal force. Normal force is n times, this is cosine theta, in the y hat direction, plus n times sine theta in the x hat direction. The weight is mg in the minus y hat direction. We have the additional friction force, which will be F friction times cosine theta in the x direction, and F friction times this side, the opposite side is the sine, plus F friction times sine of theta in the minus y hat direction. These are the forces, all the forces acting on my mass. Well, the total force, I just sum them up. In the x hat direction, I have n sine theta plus F friction times cosine theta. So these are the only forces in the x direction. Plus I have the forces in the y direction. There is n cosine theta minus mg minus the friction force sine theta this is in the y hat direction. This is the total force. My car has an acceleration in the x direction. Even in this case, it has an acceleration in the x direction. It should have an acceleration in the x direction because it is making a circular motion around the curve. And so the acceleration has to be pointing towards the center of the curve, which is in the x direction. So this total force has to be equal to m times v squared over r in the x hat direction. So I identify the forces acting on my system. I just sum them up to find the total force acting on my system. Once I have the total force acting on my system, I know that in order to make circular motion, my object should have this acceleration, so it has to be subject to such a force to create that acceleration. Now the rest is just equating the components on both sides. I have the n sine theta plus the friction force cosine theta should be equal to mv squared over r. This is one equation. And cosine theta minus mg minus the friction force sine theta. This should be equal to 0. Now my unknowns, I don't know n. This is my unknown. I'm trying to find the velocity. So these are the two unknowns I have. The friction force, the component of the friction force along this inclined direction is, since I'm looking for the maximum speed, I know that as my object goes high, has a higher and a higher speed, there will be some friction force here. And if my object goes faster, then I will need a larger friction force to prevent it from skidding on the road. But my friction force, the largest value that the friction force can have, remember it is static friction force, the largest value it can have is mu s n. So when the speed of my object is at a maximum possible speed, in that case the friction force will have its maximum possible value. If my speed is even faster, in that case, I know that in order to keep my car on the track, I need a larger friction force, but the static friction force cannot provide that friction, so it will start sliding. So friction force I know, and I do not know. I have two unknowns, and I have two equations for the two unknowns. So you can just do the algebra and solve for the velocity in terms of theta and the coefficient of static friction and g. Any questions? Any questions on this? So let's do one more example before we go on voting whether we should continue on the blackboard or with the slides. Do you know what a roller coaster is? Okay, so you have this car or train that goes on a rail, which sometimes they make such turns. So this is a roller coaster. The car, there will be some carts over here. They will be moving with some velocity at this point. And when it comes to the top of it, it will have some other velocity. Well, gravity will change its speed from point to point. So the question is, what should be the minimum speed that the cart should have at this point such that it will not fall down? This is what we would like to study. So again, first let's draw the free body diagrams. What are the forces acting on my mass? I have my mass. Let's call it M. What are the forces acting on it? There's the weight. The magnitude is mg. There is no centripetal force acting on this object. Centripetal force is the result of other forces acting on the system. The centripetal force is not a force in itself. Other forces should sum up to give me the centripetal force. There's a normal force that the rails can exert on my car. So it will again be pointing downward. Well, let us just choose the x-axis as pointing downward. The forces acting on my system is that N plus mg in the x-hat direction. This is the total force acting on my system. I want it to make a circular motion at the top point. So this should be equal to mv squared over r. R is the radius of the circle. And the normal force should also be, the total force should also be pointing towards the x-hat direction. Then what can I say? V squared, the velocity of my object, squared, is equal to r over m, mg plus n. So what do we know about this system? So this is our result, part of our result. Now we know that if the car is going very fast, it will need a large force to cause it to accelerate along this curve. So the weight is constant, the weight cannot change. The weight is this mg. So if it's going really fast, it should be the rails of this roller coaster which exerts this normal force, enough normal force so that it will follow the band. Now if the cart is going slower, then this normal force will decrease, and there might be some moment that only the weight itself is enough to bend the trajectory of this cart to follow the rails, the roller coaster. So that will be when, well, this is less than or equal to Rg. When normal force is 0, then V squared has to be equal to R times G. Or the V minimum is equal to GR. This is the minimum value of the velocity such that my cart will follow the roller coaster. If the velocity is smaller than this one, then and let's just assume that the velocity is smaller than this one, and let's just assume that the car is following this roller coaster. But it just tells me that it has if the velocity is smaller than this one, V squared over R is less than V mean squared over R. By the way, sorry. Before looking at that, let's look at one more thing. What is the acceleration of this cart when it's moving at this velocity? So the acceleration is v mean squared over r. That is equal to g. That is what we expect. Because at this, when it moves with the minimum velocity, the track doesn't exert a larger force, any force, so the only force is the gravitational acceleration, and that is g. If the car is moving slower than that, then its weight will be too much for it to follow this curve. Remember, A now, if A is constant, the magnitude of A is constant. At this point, the acceleration is, if you look at here, it is either g or larger than g. If v is smaller, then the necessary acceleration for the object to follow the track will be smaller than the gravitational acceleration. But we know that the gravitational acceleration is always there. There's no other force to reduce that gravitational acceleration, so the acceleration of the object should always be larger than or equal to the gravitational acceleration. So it cannot follow this track. To increase the acceleration, what will happen is it will follow a if the velocity is smaller than this v min, it should follow a curve with smaller radius. So if the velocity is smaller than that limit over there, what will happen is it will not follow this large curve, but it will follow a curve with smaller radius. It just means that it will not be following the track, so the cart will just fall down. In this limit, the acceleration is g. It is mainly doing a free projectile motion at that point. So at this point, if it is moving with this minimum velocity, well, the track doesn't exert a force, so it is following its free projectile motion, free horizontal projectile. So we had derived that this horizontal projectile follows a parabola. At this point, the mass is trying to follow this parabola, but this parabola matches with this circle when my object is moving with this velocity. So it will, of course, initially it will follow it, so this will be the parabola. But as it moves out of this point, the rail will start exerting additional force so that it will bend the parabola even further and it will follow this curve. The long story short, this is the velocity of this is the relation between the velocity of the object at the top point and the normal force. The minimum possible value of the normal force is 0. The railroads, unless there are clips holding it, will not pull the cart upwards. The rail at most can push it down. So that is why n is at least 0. It cannot be negative. Since this is positive, the velocity of my object has to be less than this number over here. And that tells me that the minimum possible velocity such that the cart will follow the trajectory is given by this expression over here. Questions on this one? In this case, the motion will be a bit more complicated in general. The reason why we looked at this point only is, for this point only, we can assume that it is making approximately a circular motion. But if you come here, well, it is going around the curve, but at the same time, its speed is changing. Since there will be gravitational pull, its speed will be lowering, becoming smaller and smaller as it goes up. So it is not a uniform circular motion, but it is a circular motion with changing speed. But that we will study on, well, next week.